So this is kind of like the one that you had last night. So anytime you have, this is a rational expression, you know it's going to have weird asymptotes in it. It's going to be kind of a funky looking graph. It always helps to factor anything that's not factored. So this bottom piece factors as x minus 4, x plus 2. If you need me to go over factoring with you, let me know and I can. Okay, so once you've factored it, remember you're looking for things that are alike on top and on bottom. This time I don't have any, which means I have no holes. The other name for a hole is a removable discontinuity. So this is the same thing as a hole, and this time there are none, which means every piece that we've got up here is something else since it's not a hole. The bottom two pieces are whatever's left on bottom after you've taking care of your holes. Everything on bottom is a vertical asymptote. So I have a vertical asymptote at x equals 4 and at x equals -2. So if I were going to graph this, I could go over to -2 and draw in a vertical asymptote and then also draw one in at 4. Okay, not that we're necessarily going to graph it, but if you wanted a general idea of what it looked like. Whatever's left on top after I've taken care of vertical asymptotes and holes is my x-intercept. So I have an x-intercept at 6. You solve it, by the way. X minus 6 equals 0, so x equals 6, which means at 6, it's going to cross the x-axis right there. So the other thing that we didn't talk about that wasn't asked on that was about the horizontal asymptote. So you remember I showed you the parent function always has a horizontal asymptote at the x-axis, but it might be different. So the way we determine that is to compare the degrees. The degree is the highest exponent of each polynomial. So the highest exponent of the top is just 1 because there's a 1 with that x. And the highest exponent on bottom is a 2. When you compare them, we have a little saying is Bobo Botten eats DC. And that stands for bigger on bottom, 0. Bigger on top, none. And if the exponents are the same, divide coefficients. So in a little bit, I'll just give you a couple and we'll just look at the horizontal asymptotes just because that's a super easy thing to do and that'd be an easy way to get a problem right. So I'm comparing my 2 degrees, and in this case, my degree is bigger on bottom. That's Bobo, bigger on bottom, 0. So my horizontal asymptote is still at 0 like we originally thought. Now, remember I told you an asymptote is an imaginary boundary line that the graph cannot touch or cross. It gets closer and closer to it. And here I just drew a horizontal asymptote right through the x-intercept, which I said was going to be there. That is because the horizontal asymptote applies for much of the graph, but not always all of the graph. Now, that is never true of a vertical asymptote. Vertical asymptotes always apply, but horizontal asymptotes can. So this graph is probably going to look something like that. It's going to go through that last piece. And I'm not sure. Let's see, what is our y? Okay, so if you look, our y-intercept, remember your y-intercept is if you plug in 0 for x. So that means all of these would be gone, and I would be left with just -6 over -8. So positive 3/4. So that means I have a y-intercept right here. More than likely, this probably looks like this. I'm not for sure, but that's my guess. And then I don't have an x-intercept on this side, but I'm guessing it probably looks like that because I look at graphs a lot, so I'm just guessing, but it doesn't really matter. I was just going to show you how to find the horizontal asymptote as well. So I'll get a couple and we'll try a few.